Alright class, today we're going to talk about section 4.4, which is on optimization problems. And this is basically taking all of our max-min ideas in calculus and actually applying them to real-world problems. So you can think of, for example, a very simple example you've probably seen before. If you fire a cannonball into the air, you could use calculus to find where the maximum height of the cannonball would be. Another example would be, say you are a sales analyst and you get this formula that shows you the company's profit based on the price of the goods you're selling, and you want to maximize the profit, obviously. Or say you have a cost function, and often you will want to minimize the amount of cost that the company accrues over time. Okay, so there are a lot of examples out there. The word optimization is just a catch-all for both maximizing and minimizing. So, some things you'd want to minimize the amount of materials used to make an object, or maybe you want to maximize the amount of volume that maybe a can could hold. Provided it has to hold a certain amount of volume. Okay, so that's the idea of this section, and you can probably already guess how you proceed. If you have a formula that will give you volume or cost or whatever, you just take the derivative, set it equal to 0, solve, which gives you the critical point or critical points, and then from there you can find whether it's a max or a min, and that's, your nice spot. What we are going to use in this section, what's very helpful, is this little theorem right here. You can see it, okay, which says that basically if you have a single local extrema, so if you have a single local max or local min on an entire interval, right? So say you find the critical points and you only find one, then that, if it's a local extrema, local max or local min, it has to be the absolute max or min. Okay? And that's basically what this says, that if we only find a single critical point, then that critical point must correspond to an absolute extrema. And if you think about that, why that might be true, say I find a single local max, and that's the only critical point I found, that's the only local extrema I found, well, that means the function's not allowed to turn around again, meaning it must be the absolute max. All right, well, that's where that basic idea comes from. So we're going to use that to really help us, because in a lot of these problems, we're going to only find one absolute, one critical point. And so that critical point from this theorem, I didn't write the theorem explicitly here, but this theorem basically tells us if we find that one critical point, then it must correspond with what we're looking for. Okay. All right, so we'll start with an example here. Let's say we have a sales analyst that determines that the revenue from sales of a product is given by this function here. R of x equals negative 50x squared plus 250, where x is the price charged. Both of these are in dollars. Okay, so the price charged per item, and this is with x between 0 and 5. All right, so then the question is, what price should the company set for this product? All right, so we have this x trapped between 0 and 5 because, well, if you think about it, 0, you can't have a price less than 0. Right, it doesn't make sense. You can't charge negative amounts for things. And 5 is actually a good place to stop. And basically, it's because if you were to plug 5 into here, you'd get 0. But that's just, we're given an interval to work with. So when we're given an interval to work with, remember, if we want to find the absolute maxes and mins, we just find the critical points and the endpoints, plug everything in, and see which is the highest. Okay, so to go about doing this one's actually pretty simple since we've been given the formula. A lot of these problems we won't be given the formula. We'll actually have to determine it somehow. So to do this, we're going to start by taking the derivative. Right, so we're going to use calculus here. So the revenue function r of x is negative 50 x squared plus 250 x. Okay, so we'll take the derivative. We'll get negative, sorry, not 200, negative 100 x plus 250. Okay, so to find the critical points, we set this equal to 0. I get a negative 100 is equal to negative 250. So x is equal to 250 over 100, which is basically $2.50. Okay, so here's the critical point. And basically, we could stop here, okay, because this is clearly going to be the maximum, but let's go ahead and see. If I plug in 0, right, if I plug in, I have the function up here. If I plug in 0, I get 0, 0, so this thing becomes 0. Okay, that should make sense. The revenue should be 0 if we don't charge anything. If I plug in 2.5, okay, 2.5 is going to be negative 50, 2.5 squared plus 250 times 2.5, and that, let's see here, let me plug that in my calculator. I got $312.50. And if we plug in 5, okay, so negative 50, 5 squared plus 250 times 5, what we get again is 0. So this is definitely the max. So the max revenue, okay, is it occurs when we charge $2.50 for whatever this product is, and we get a revenue of $312.50. Okay, now some of you might have thought, well, since we're on the interval 0 to 5, and we have 0 and 0, shouldn't the max occur at 2.5? You just divide, take the half of the interval, and the answer to that is that's only true in very specific cases. I mean, this revenue function just happens to look like a nice curve, but often revenue functions will instead look something like this, and we have no idea where that maximum ends up being. So you do have to go through this process. Even if you speculate, okay, even if you speculate, you have a conjecture that, oh, the answer is probably going to be 2.5, you still have to show why, okay? You aren't just finding the max and great, you found it. You actually have to show why it's the maximum. All right, so we're not just finding, we're showing. So we're not just finding the answer. We're showing why it's the answer. Okay, that is a big deal. Don't expect anybody to trust you. Don't expect anybody to believe you without evidence. Okay, the farther you get in math and science, the farther you get away from just being able to say, hey, this is the answer and this is what I say is true. No one's going to believe you. You have to prove what you say is true. Right? You have to have evidence. You have to make a point. And in math, this is how we make our point. Okay? Let's look at another example. Okay, so this is a geometry example. There are a lot of those in this section. In fact, the majority of the things you'll see in your book are geometry problems. All right, so let's say, we'll start simply. Let's say a farmer wants to fence in a rectangular area against a river. Okay. If he only has 100 feet of fencing, then what is the maximum area he can enclose? So here's basically what's happening. We have the river. Let's assume it's a straight line. Okay. And then we're going to enclose a rectangular area against the river. You could also set up this problem against a barn, against whatever. Okay. And we only have 100 foot or 100 feet of fencing. Okay, so this is actually the fence here. So this, let me put this in a different color. I don't really have blue, so this purple will have to do. This purple's the river, so this is not part of the fence here. So the only part of the fence is going to be this length, and this length. Okay, so what we're trying to do is, I know that this, and this have to add up together to be 100 feet, right? That's how much fence I have, and we want to maximize this area in here. Okay. So how we're going to do this is we want to maximize the area. So what is the area? Well, the area, if I label this as, let's say that this is the length and this is the width, I have width by length by width, okay? But the area of a rectangle, it's still a rectangle, the area is still going to be length times width. Okay? Now, I want to maximize this thing. But in order to do that, we have to take the derivative, and in order to do that, we need to get this in terms of a single variable. All right, so I want this just in terms of a single variable. So just L or just W. Okay. And to do that, well, what's the other piece of information that we have? Okay, well, we have we have 100 feet of fencing. So if I take this W and this L and this other W, right, they should add up together. So if I take L plus my two W's, add them together, what should that end up equaling? Go ahead and have a guess. Well, of course, it should be 100 feet. Okay, and now that I have this, I can actually get this L in terms of W or W in terms of L, and I'm just going to solve it in the simplest way, which is just move the 2W over, because in the end, it doesn't matter. Right, so L is equal to 100 minus 2W. It's always best to just solve for whatever's easiest. And now, I have L equals 100 minus 2W. If I put that in, replace L with 100 minus 2W, I now have a function A, which is the area, okay, which is it's a function of a single variable. It's now A of W. It's now a function. So it's equal to 100 minus 2W all times W. So when we distribute that, it's 100 W minus 2W squared. Okay? And the reason we did all this is because now, if I want to maximize A, if I want to find the maximum, I want to start by taking the derivative. Right? And the derivative, 100W minus 2W squared, is going to be 100 minus 4W. Okay. And now, to find the critical point, we set that equal to 0, and we get 100 is equal to 4W, which gives me that W is equal to 25 feet. Okay, and we're not done because we're asked to find the actual, what is the maximum area you can enclose. So we found the width. So we found that this width here is going to be 25 feet. So 25 feet, 25 feet. So here we have 50 feet. So what must L be? Must be 50. Okay. Or you can actually plug this W back into L here. So L, let's do that underneath. If W is 25, L is going back to here, 100 minus 2 times 25. So that will be 100 minus 50, which is 100 feet. Or sorry. That will be 50 feet. Okay, so that's L. So you can either find that just, obviously, L is 50 feet, or you can just plug it back in. Therefore, that area, the area is still L times W, it's 25 times 50. Okay, so the area, the maximum area, I'll write it here, maximum area. Is 50 feet by 25 feet, which is 1,250 square feet. Now you might be thinking, well, hold on. You didn't check to see if this was actually a maximum or a minimum. Okay. And, okay, well, the reason is because basically just the way the problem is set up, it has to be the maximum, right? If a maximum exists, so the reason we didn't check, okay, so the reason we didn't check is because we found one critical point. You can only do this if you only find one critical point. Or if you only find one critical point, that makes sense, right? Sometimes you might find a positive and negative critical point, and the negative one makes no sense. So the positive is the only one that works. Since we found one critical point, okay, if a max occurs, then it must occur at when W equals 25. Okay, it has to. And it's not going to be a minimum, because a way you could get a minimum area is if you let W be 0. Right? If W is 0, you would just have this line here that's 100 feet long, and you would have no area. Right? So the minimum area is actually going to be 0. So we found something at 25, and that gives us a positive value, so that has to be the maximum. So this really only works if you find a single critical point, and a lot of these are going to be that way. So once you go through all this process, we don't really check using a rule or a test, because just the way it's set up, that has to be the answer, and if it's not, then it just doesn't have a maximum. Okay. Okay, so to set up these problems, it basically follows the same rules, the same process each time. Okay, basically, one, you identify the quantity to be optimized. Okay, are we maximizing the area? Are we maximizing the volume? Are we minimizing the perimeter? Are we minimizing the surface area? You identify whatever quantity that is and start with its formula, right? It will have a formula. You're going to start with that, and it will probably have a couple of variables in it. Then 2, you use other information to get this formula as or in terms of a single variable. Right? Well, we can't use the product rule here. I mean, we could, but it doesn't make any sense. This isn't related rates. These quantities aren't actually changing with respect to time. We're actually trying to find where we should fix them and find the maximum. So you've got to get that formula in terms of a single variable, and I say use other information because you'll be given other information about something else, either the perimeter or surface area or whatever. You're given some other information, and you need to take it and solve for one of the variables, right? You want to isolate the variables. So this is also known as isolate a variable. Then once you do that, plugging back in, well, I've already done that if you're getting that in terms of a single variable, but now we can take the derivative. Right, now we can differentiate. And once we do that, then it's just a matter of setting equal to 0, solving, doing all that, finding your critical points, yada, yada, yada. But it's the setup that I think gives most people problems. And it's just, you identify what you're trying to optimize, then you try to get it in terms of a single variable, and you're going to use the other formula to do that, right? The other given information. And then once you get it down to a single variable, then you can differentiate, set it equal to 0, solve. All right? So let's look at another example. Okay. So let's say, that just about fits. Let's say a farmer, and it's going to be another fencing farmer problem, but these are good to start with. And let's say a farmer wants to enclose an area of 1.5 square kilometers in a rectangular field, and then divide it in half with a fence parallel to one of the sides of the rectangle. Okay. So how can he do this and minimize the cost of the fence? So here's basically what we're told. So we have a farmer who wants to enclose an area of 1.5 kilometers squared. So one way you can approach these problems is just start by writing everything you're given in terms of mass. So we have the area is 1.5 square kilometers. So I have that the area is 1.5. Okay, so that's the first thing. All right, and then we're told a rectangular field. So he wants to enclose an area in a rectangular field and divide it in half with a fence parallel to one of the sides of the rectangle. So basically we have a rectangle. That's what we're wanting to enclose. And then we want one of the sides to be parallel to the other side. So he's cutting this, he's dividing it in half. Okay. All right. Then we're asked, how can he do this and minimize the cost of the fence? So the cost of the fence, well, we don't really know how much fencing costs, but if we minimize the amount of fence that's actually used, right, we can actually minimize the cost. So we're really minimizing the fence. All right, so there are a few ways to do this problem, but I'm just going to start labeling my lengths. All right, I'll label this y and this length x. Okay, so I have y, y, y. I have x, 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 x. Okay, so what I have is basically the amount of fence. I'm going to call F for fence. There, you could just say P for perimeter. But basically I have 3 Y's and 4 X's. Okay. Now this is what we're trying to minimize. Trying to minimize the amount of fence. Okay. All right. Now, what we want to do is get this in terms of a single variable, and we do that by using this information here. Okay. So there are 2 ways we can do this. All right. The first is we could say that the whole area of this entire rectangle is 1.5, and that's a y by 2x rectangle. Right, so you could either say, oh, I have a y by 2x rectangle, and that's equal to 1.5. Right, that's the area. Or you could take the area of just a half region, right, because we're splitting it in half. And if we split 1.5 in half, this region must be 0.75 square kilometers. So this is a y by x, right? So the area of the red region I did is a y by x rectangle, and that's equal to 0.75. And check this out. If I started either way, it doesn't matter, because here, if I have y by 2x, 1.5, if I divide both sides by 2, I get y times x is equal to 0.75. So it really doesn't matter all that much. Okay. All right, now the question here is, which do we solve for? So now we're going to solve for x or y. We just want to get, we basically want this guy in terms of a single variable. And at the end of the day, it doesn't really matter which one we go for. We could do either. I think I'm going to solve for x. All right, so x, we just divide both sides by y. So I get 0.75 divided by y. Okay. It doesn't matter. You will get the same thing out no matter which way you go. Okay, so I'm going to take this and plug it in for x. And so I will get now a function of f, or a function of x, f of x, or sorry, it's actually a function of y. So function of y, 3y plus 4 times 0.75 over y. All right. Now I chose to solve for x mainly because I know 4 times 0.75 comes out to be a nice number. I know that now that f of y is 3y plus 4 times 0.75 is 3, so this is 3 over y. And now I'm ready to take the derivative. Okay, so now we're going to differentiate. Alright, so f prime of y is going to be 3. And 3 over y, when we differentiate, that's going to be negative 3 over y squared. I'm doing that really fast, but basically if you want, you could change this to 3y plus 3 to the y minus 1 and use the power rule. But again, like I said, for these applications, I'm going to be doing these a lot quicker than I was back in chapter 3. See if you can take the derivative and get to that. You should be able to, okay? You should be able to do these derivatives really quick by now. All right, so if you forgot them, you're in trouble. All right, now we're going to find critical points and find the first thing I'll note is that this thing, f prime, is undefined at 0, right? So f prime is undefined at y equals 0, but it's not going to be a critical point because that 0 doesn't make any sense, right? If I made y equal to 0, I wouldn't have a rectangle anymore, so we're not going to really bother with that. And that you could actually consider that one of the endpoints, so we don't have to worry about it. It's still something to keep in mind whenever you're doing this. But I'm going to set this equal to 0, no problem. And I'm going to move that over. I get 3 is equal to 3 over y squared. So basically now I have, if I move the y squared over, I get 3y squared is equal to 3. Okay. In other words, y squared is equal to 1, which means y is equal to plus or minus 1. But minus 1 makes no sense in this case, so y equals 1, and we're in kilometers here, is what we want. Okay. Now, we're not totally finished yet. We're asked, how can he do this and minimize the cost of defense? So I also want to find x, right? So I know that y needs to be 1 kilometer, so x, if we go back to what x equals, x is 0.75 over y, so x will be 0.75 over 1, so 0.75 kilometers. So that's how he can do it. He can minimize the amount of fence he uses by letting y equal 1 and x equal 0.75. So I don't know about you, but that's not actually something I would have guessed just looking at this problem. But with calculus, it actually comes out to be a not too difficult solution, really. Okay. And I'll bring it back to this screen before we move on. All right, the last example I really want to consider today is a three-dimensional one. Right. So what we're going to look at here is I have 125 pi cubic meters of water is to be held in a cylindrical tank with an open top. What dimensions will minimize the surface area of the tank? Okay. So first of all, I have a cylinder, right, a cylindrical tank. So I'm going to draw my picture here. And I know the amount of volume that's going to be held in this tank. So the volume I know is going to be 125 pi cubic meters. But I also know that right, a cylinder is broken into H and R. I might as well go ahead and label those. So volume is, the volume of a cylinder is pi r squared H. Okay. Now, this is not what we're trying to maximize or minimize, but it is a piece of information we're given here at the first sentence. This first sentence gave me all of this information here. Okay. Now, what dimensions will minimize the surface area of the tank? So now we're talking about surface area. So we want to minimize surface area. Okay. Now this is a very common problem if you think about it. I have a cylinder. So think about, say you're Coca-Cola, right? And you want to manufacture cans to ship your Coke in. Now each can has a fixed amount of Coke inside it, right? You don't really change the amount of Coke. You could, but say the standard is you're going to ship this a specific amount of Coke. And what you want to do is you want to So you can't change the cost of making the Coke at this point. The Coke's already been made. You want to put it in cans. So you want to actually minimize the cost of making the cans. So what you want to do is minimize the materials used. And that's exactly what this problem is saying. Say we have a can, and this is specifically a tank. We want to minimize the materials of that tank, and doing that is basically a surface area problem. Now, this isn't all that realistic because, you know, a tank would actually be a three-dimensional object. You know, even if it was cylindrical shape, it would be like a cylinder within a cylinder and whatnot. But baby steps, right? We've got to start with the simplest type of problem. But when you take a step further and get to those optimization problems that companies actually do, it will be the same thing we do here, just at a more complicated scale, right? They're going to do the same steps. Okay, so surface area. Well, the surface area, that's a formula a lot of people forget, but basically what we have is this object is made up of two things. We have two circles and a rectangle that goes all the way around. Okay. Now, we're told that we have an open top. So we have this circle, but we don't have the top circle. So the surface area, which I will call S, some people call it A, but I'm just going to call it S for surface area. It's going to be the area of the base circle, okay, plus, now this is the sides. I'll call it the outer sides. All right, so the area of the outer sides. Now, yes, you could just look up this formula, but I'm showing you how you find it without it, because the surface area stuff is something a lot of people forget the formulas for. I don't have them memorized, you know, usually, but I can find them pretty quickly. Now, this is taking a while, but I'm actually explaining it to you, so that takes longer than just doing it yourself. All right, now the area of the base circle, that's just going to be pi r squared, right? That, no problem. And if I had both of them, if I had a top on this, it would just be two of these. You'd have two, the area of the base circle, the area of the top circle, it'd be 2 pi r squared. Okay. Now, the area of the outer sides, this is essentially a rectangle. Imagine, I mean, if you have if you have a cylinder, I'm trying to see if I can show this on the camera here. Say I have this cylinder here, right? Sheet of paper that I just rolled up to be a cylinder. Now, if I cut it along this line and fold it out, what do we have? We actually have a rectangle. Okay, so this area of the outer sides becomes a rectangle. So imagine cutting this and spreading it out, and it will give you this rectangle. Okay, and the side here, let me use colors here. The side here that I cut is, say, right here, and that is what value? Hopefully you guessed the height. That will be the height. And then this length here, okay, well, that is this length around the circle. Okay? And that's the circumference of the circle. Right? That's the circumference, which is 2 pi r. Okay, so this is a 2 pi r by h rectangle. So this area, right, I'll say the area of this rectangle is going to be 2 pi r h. Okay, so the area of the outer sides is 2 pi r h. And you can do this for any shape if you're trying to find the surface area. If you had a box, that box is made up of a bunch of rectangles. So you just take the area of all those rectangles. Okay? All right, now I want to get this thing in terms of a single variable, right? Because this is what we're trying to minimize. So we want this as a single variable. Okay, so that means we're going to go back up to this formula here. I have pi r squared h is equal to 125 pi. All right, so the first thing I'm going to do is divide by pi on both sides to get 125 is equal to r squared h. And then I'm going to pick whatever's easiest to solve for. Now what's easiest to solve for is h. If you solve for r, you would divide by h and then you'd have to take the square root of this thing. I don't want to do that, right? I'm just going to divide by r squared and give me that h is equal to 125 divided by r squared and use that. All right, so I'm going to put that in for h. All right, so let's use red here. So it pops, I'm going to put that in for h. Okay, so now I have a formula just in terms of r. So I have s of r is equal to pi r squared plus 2 pi r, and I'm going to put in 125 over r squared. All right. Now I'm going to simplify this a bit. All right, so I have s of r is pi r squared plus this r will cancel with one of these down here, and 2 times 125 is going to be 250. So this is 250 pi over r. All right. And now, what do we do? Now that I have this formula, s of r, well, we take the derivative. This is going to be s prime of r is 2 pi r minus, again, this is the same thing here, it's going to be minus 250 pi over r squared. We take the derivative. Right, this thing you could write as 250 pi r to the negative 1 and do it that way. Okay. I'm just saving time because I want to talk more about the maximizing than taking derivatives. And now we're going to find the critical points, right? But I'll start by saying, note, right, s prime is undefined, or I'll just say s prime does not exist. That's a little easier to do, D and E, at r equals 0, but r equals 0 makes absolutely no sense, right? If you want to hold this much water in a tank, if you make the radius 0, you don't even have a tank anymore, so we won't worry about that. But it's always good to consider. Now, we're going to set this equal to 0. A lot of ways you can do this, but I'm just going to move this guy over. So I have 2 pi r is equal to 250 pi over r squared, and then multiply both sides by r squared, because it will cancel the r squared here and just move it over here. So I have 2 pi r cubed is equal to 250 pi. Okay, that gives me that r cubed is equal to 250 pi over 2 pi. So the pi's cancel, and 250 over 2 will get us right back to 125. Okay, so that means that r is equal to the cubed root of 125, which is 5, and our units are in meters. Okay, so there we go. I found that r is equal to 5 meters. All right. So from here, now remember the problem, we're almost done, not quite. What dimensions will maximize the surface area of the tank? So we need the dimensions, so we need both r, which we have, and h. So I'm going to use this formula to find h. H, remember, is 125 over r squared. So in this case, it's going to be 125 over 5 squared, which is 25. So it's 125 over 25, which is also 5. Okay, that's kind of interesting. I have the height and the radius will be the same. So it's actually, if this is 5 meters for the height, then the radius will also be 5 meters. But that actually means that it looks something like this. Right? So it's a tank, officially that is 10 by 5, if you're talking about diameter by height. Okay, and again, I don't really use a test to check to see if this is actually the minimum. If a minimum occurs, it has to happen here. Okay, at this point. All right, and that's about it for talking about this. Remember, just take these slowly. Try, set up your formulas from what you're given, and then you're always going to be plugging something in. You're always going to try and get that formula down to a single variable, and that information will always be given to you. All right? Cheers.